Hi, welcome back to Circles Part 2, Lesson 7, Proportions. And at the end, there are going to be a few review questions, and then Lesson 8 is actually dedicated to review along with a very small concept being introduced. Okay, we're going to hop right into Lesson 7 on proportions. Okay, how do proportions fit into area and volume of a sphere? And this is how it fits in. Okay. I'm going to first go over the concept of a linear measurement. When you are looking at a sphere or a circle, your linear measurement is the radius or the diameter. So we're going to call that just in relation to x or r or d. And then if we're finding the area of a circle, or in this case a sphere, surface area, we will square to find the area because it's two-dimensional. But then when you find the volume, you're going to cube your radius or diameter. You're going to cube your linear measurement to find that the volume. So the relationship is the linear measurement is always the radius and the diameter. The area is always squared, and the volume is always cubed. Okay, so how does that relate to two spheres? Okay, so let's take a second. Let's say that we have two spheres, and here, let me cover this part up so you can only see one at a time here, but you should have it out anyway. Okay, we're looking at the one that has a 1 to 3 relationship. So we have two spheres, one that has a radius of 1 and one that has a radius of 3. Okay, what's going to happen to the ratio of the areas? Well, the areas are not going to be in a 1 to 3 ratio. We're going to take that ratio and we're going to square each part to find the ratio of the areas. So if the radius or the diameter are in a 1 to 3 relationship, the areas are going to be in the 1 squared to 3 squared or 1 to 9 ratio, because we're going to take that area and we're going to square it. Okay, now to find the ratio of the volumes, we're actually going to go back to the original linear measurement and we're going to cube them. So instead of being a 1 to 3, we're going to have a 1 cubed to 3 cubed, which is what? 1 to 27. So the volumes are going to be in a ratio of 1 to 27. Okay, so let's look at a second example of that. Okay, again, we have two spheres. Their radius or diameters are in a 2 to 5 ratio. So when I say 2 to 5 ratio, they actually could be 4 and 10, but they reduced to 2 to 5, or they could be 6 to 15, and again, reducing to 2/5 ratio. Okay, what's the ratio of the areas? Well, to find the ratio of the areas, I will square each part. So I'm going to get 4 to 25 is the ratio of the areas. How about the ratio of the volumes? Well, I go back to the linear measurement and I cube them. So 2 cubed to 5 cubed. 2 cubed is 8, 5 cubed is 125. So the volumes are in a ratio of 8 to 125. Okay? So let's look at one where we are not given the ratio of the linear measurement. We're given the ratio of the areas. Okay, let's say we know the ratio of the areas are in a 25 to 36 ratio. What would be the ratio of the diameter and radius, and what would be the ratio of the volumes? Well, first we have to go backwards and find the linear measurements. Well, if it's 25 to 36 and we squared the linear to get to the area, we're going to square root it to work backwards. So the square root of 25 is 5, and the square root of 36 is 6. So that means the radius and diameter in a 5 to 6 ratio. Now we can go figure out the ratio of the volumes. We can just take the linear measure and cube them. Okay, so this one's going to be 125 to, what is 6 cubed? I believe that is 216. Let's see, I might be wrong. 2, 6 to the 3rd. Yeah, 216. Okay. So they're in a 125 to 216 ratio. Okay, so that's how you work it when you're given the ratio of the areas. You work backwards to the ratio of the diameters and the radius, and then you take that and cube them to find the ratio of the volumes. Okay, let's look at one where we're given the volume. Okay, so we have a 1 to 8 relationship of the volumes. We want to figure out the ratio of the areas and the ratio of the diameters. Okay, what we're going to have to do is we're going to have to undo the cube, which is cube rooting. So what's the cube root of 1? Well, the cube root of 1 is just 1. What's the cube root of 8? Cube root of 8 is 2. So we have to work backwards to the linear measurement first, and then we can take that and square them to find the ratio of the areas. So it's in a 1 to 4 ratio for the ratio of the areas. Okay, so let's look at this one. Okay, let's say we're given the area is 8 and the area of the other one is 50, and we have to figure out the linear measurement and the cubic ratios, those ratios. Okay, notice that 8 and 50 are not perfect squares. So, but we can reduce them, and what can we reduce those to? An 8 to 50 ratio actually reduces down to 4 to 25. Now 4 to 25, those two are perfect squares. So now we can find the linear measurement. So a 4 to 25 becomes a 2 to 5 ratio, which is, that cubed would be 8 to 125. Actually, that's the same as number 2, isn't it? But that's all right. You were just given different information. You had to work a different direction. Okay, so let's look at some application problems here on surface area and volume when the radius changes. Okay, the first one. A balloon has a radius of 6. Describe what happens to the balloon's surface area if the balloon inflates and the radius changes to 12. Okay, so what type of ratio is the original balloon, and then once it's blown up, what's in a 6 inches to 12 inches? So it's in a 1 to 2 ratio once we reduce it. And that is a radius. So that means we're on this linear column. We know that the linear measurement is a 1 to 2 ratio. So what would be, the question says, describe what happens to the surface area. So we're only going from linear to the area. Okay, so all we have to do is square these to find the ratio of the areas. So 1 squared and 2 squared gives us a 1 to 4 ratio of the areas. Okay, so if a balloon has a radius of 6, describe what happens to the balloon's surface area if the balloon inflates and the radius changes to 12. Well, the surface area is 4 times as large. It's 4 times bigger. Okay? It's 4 times the original surface area of the first one. So if the first one has a surface area of 10, then the bigger one has a surface area of 40. It's 4 times bigger, the surface area of the original. Okay? And as you do more of these, it'll make more sense as we practice these. Okay, describe what happens to the same balloon's volume this time, if the radius is doubled. Okay, so we had that same balloon. We had 6 to 12, which we decided was a 1 to 2 ratio, which just means it does double. Okay, so we're talking about the same balloon. So what's happening to the volume? Well, the volume, we're going to take this ratio and cube it. So let's cube 1 and cube 3. So it's going to be a 1 to 8 ratio. So the volume will be 8 times greater than the original. So if the volume of the original balloon was maybe 3, the volume of the larger one is 24. It's going to be 8 times as large. Okay, let's look at number 3. A sphere has a radius of 4. What happens to the sphere's volume if the radius is halved? Okay, so let's think about that. So we have a 4-inch radius, and if it's in half, it shrinks down to 2, doesn't it? Okay, so we have a 2-to-1 ratio instead of a 1-to-2 ratio. It was larger, now it's smaller. What happens to the sphere's volume if the radius is halved? So let's take that, and since we're dealing with volume, we're going to cube this ratio. So this is going to be in an 8-to-1 ratio. So what's going to happen? The volume gets smaller this time by what? By a ratio of 8. So the volume gets smaller 8 times, or 8 times smaller, I guess I should say. Okay? So that's just one. Same idea, you're just working it from a large sphere to a small sphere, so it's actually reducing. Okay, a sphere has a radius of 8. What happens to the sphere's surface area if the radius is halved? Okay, so we have 8, and half of that would be 4. So again, we're going from a large to a small. Let's reduce that ratio. That's going to be a 2-to-1 ratio. What's going to happen to the surface area? Well, surface area is our square, isn't it? It was the one in the middle of the chart. So we're just going to square that. So 2 squared to 1 squared is 4-to-1. So what's happening to our surface area? It's not getting bigger, it's getting smaller. By how many? By 4. So the surface area is reduced by a factor of 4. Or it's 4 times smaller. Okay?